calculator. We're going to do a bunch of the notes today very quickly. The ones that I'm really wanting you to make sure that you understand and know, I will slow down on. The rest of them, if you don't get them, you can go ahead and get up and watch the rest of it to get it if you need to. All right. I had on my notes that we got to this page. Did we do both of the things on this page? Yes? Okay. So we're moving forward. Well, part of the board is working. That's fun. Okay, so we're going to move forward. I guess I'm going to come over here. So kinetic theory has to do with gases and how they interact with the walls, with each other, and how that affects the pressure. Over here we have bromine. Bromine is a distinctive gas. It's brownish, red, and you do need to know that. So I'm going to be giving you some ways to remember all these things. And one of the ways that you remember the kinetic molecular theory, the short version, is with toddler rules. Anybody that's 5 and under is considered toddler, and there are 5 rules. And these all you can refer to toddlers to remember them. So these refer to ideal gases. And everybody loves a toddler. They're just so cute and so sweet. So they're ideal. First one is they have no volume. Okay, just go that way and just open it. They have no volume. They have elastic collisions. In other words, when they get up and they're trying to toddle around and walk around, sometimes they fall down and they bounce back up. They are in constant, random, straight line motion. If they see something they want, they head right to it. Once they play with it, they look around and see something else they want, and they head right to it. It's a constant, random, straight line motion. You couldn't guess which way they're going. They don't attract or repel each other. I like to tell the story here about my son when we were in the grocery store. He had never seen anybody with tattoos on him. And, you know, as a mom, you're telling your kids, don't write on the walls, don't write on this, don't write on that. Well, he popped up and he says, Mom, his mom is going to be really mad at him. He wrote all over him. So, and of course, the guy goes, okay. But they just say what they, they're not attracted or repelled by anybody. They have an average kinetic energy related to the Kelvin temperature outside. So in other words, their energy is related to the temperature. If it's nice outside, they want to be outside swinging, sliding, playing with sand, doing stuff outside. If it's cold, they want their blanket and they want a Disney movie on and they want to snuggle. So I'm going to go through these really quick again as a review. So they have no volume. They're able to sit on a parent's lap and don't have to pay for a ticket. They have elastic collision, so when they're walking and they fall down, they get right back up. They're in constant random straight line motion because they're always checking out new and exciting things they think are exciting. They are not attracted or repelled by each other. They're just curious. Okay? And they have an average kinetic energy related to the Kelvin temperature outside. So hopefully you got those down. Are we ready to move forward, or are you still writing? Okay? So remember your toddler rules. That's the ideal gases. Okay, now, not everything is ideal, so we get to real gases. Real gases are like teenagers. This is the teenage rules. Okay, these are particles in real gases. They have their own volume. They need their own space. They are attracted and repelled by others. And they found out collisions are not elastic. They've had driver's ed. Now the problem becomes when we're working with gases in lab, we want them to act ideal. But they are real gases. So how do we get real gases to act ideal? This is, well, how do you get teenagers? How do you get teenagers to act ideal? Make sure you bring it back to me. Thanks. Well, they behave most ideal in the summer, where they're at low pressure, high temperature, and they can choose who they hang with. So they're in nonpolar molecules. So reviewing really quickly, real gases are, they have their own volume. I need my own space. They're attracted and repelled from each other. And they've learned that collisions are not elastic. And to get those real gases to behave more ideal, it's summertime. Low pressure, high temperatures, and with my friends. Nonpolar. I don't have to be in a class with somebody I don't like. Okay, we ready to roll on this one? Anybody need a few more seconds? We got it? Okay, so we're going to define these. You do not have to write every word that I've got up there down. Just make sure you got a main idea of what each of these are. So kinetic energy is basically the energy of motion. We get this energy of motion by kinetic energy is equal to, you're going to have to lock it back up, aren't you?
No, it's just a push lock.
It's just, but you have to turn the key.
I don't think so. Try that.
I think so.
Do you want me to keep them?
Keep them, lock it up, and bring it back. Okay. The energy of a particle has the resulting motion. So we use kinetic energy equals 1/2 mass times velocity. That's not volume, that is velocity. And it will increase with the temperature. So kinetic energy increases with temperature. And that's one of our toddler rules. Okay? Potential energy is the stored energy. So when you have potential energy, it's stored energy. Kinetic energy is energy of motion. So it's what's stored because of attractive and repulsive forces that are acting on it. Then we have cohesive forces. These are related to potential energy. These are the attractive forces between particles. It's associated with potential energy. Disruptive forces are associated with kinetic energy, and these are the forces that result because the particle's moving. I'll wait till the head bob slows down a little bit. Like I said, you don't have to write it exactly in the words that are there, but okay, go ahead and moving forward. So the equation for kinetic energy we're going to be using a lot. You need to remember it. Kinetic energy equals 1/2 mass velocity squared. So if we were looking at this boy and he tossed this ball up in the air and it came right back down to him, as it's going up in the air, what kind of energy is this? Kinetic. When it gets to the top, before it comes back down, what kind of energy am I at? Potential. And when it comes back down, I'm kinetic. Good. So we have an experiment here, not experiment, a problem here that is a football problem. If I have a halfback that is 180 pounds and he is moving this way, so he's 180 pounds or 81.8, yes, that was good. My badge made it go forward. 81.8 kilograms. And he is moving at 8.0 meters per second. This is not going to be fun. I have to keep coming back and forth. I wonder if it was my glasses this time. Okay. I just pulled them off the thing. And the other person is, what is it, a tackle? Yep, a tackle. And the tackle's moving this way at 3 miles per hour. Okay, we're not doing this. I'm done playing this game. I'm just going to do it over here. I've been having problems with my board all day. And this guy is 260 pounds. We're going to be using the kinetic energy. I'm just going to type. So kinetic energy is going to be equal to, for the halfback, I'm just going to put halfback, is going to be equal to 1/2 times the mass, which is 81.8 kilograms, times his velocity, which is 8.0 meters per second. And I'm going to square that last one. And we'll get an answer for him. For the next one, for the tackle, so the kinetic energy is equal to the tackle is 1/2 times his mass, 118.2 kilograms, times his velocity, 3.0 meters per second, and that is squared. And we can find out how much kinetic energy each one has, so we can see which one has the most kinetic energy to push the other one back. So somebody got the calculator for the first one up here. Shout it out when you've got it. 2617.6, so that would be 18, right? Unit joules. Do I have a second on that? Okay. Going for the second one down here. 532 joules. Okay, so what does that tell me? This is a heavier guy, right? But he doesn't have enough energy, so the halfback is actually going to push back the tackle. Right? Okay, so let's go on to the next one here. With all my little oopses there. Whoops, going back. Yes, that is not forward. That is... There we go. Which would have greater kinetic energy? Hydrogen molecule traveling with a velocity of 2v or a helium molecule traveling with a velocity of v? We're going to do the same kind of setup that we did in this other one, but instead of putting the actual number here, we're going to put 2v, and instead of being given the kilograms, we're going to be just putting the mass of that, and this will be hydrogen, and this one down here will be helium, and helium's mass is 4.003, and it said that we had just a v for velocity. So we're going to need to find some new numbers. What do we get for the top one? Oops. This is what I got. Does everybody agree with that? Did I do my math correctly? For the bottom one, I think it's 8.012, I think. Is that right? V squared. Somebody help me. Mathematicians. Did I do that wrong? I think I did that wrong. Me either. How much did you get? It was 0.1. 0.15. E squared. Yep. You're right. I think I just times the 2 and the 4 instead of doing divide. The top one would be what?
The 1/2 and the 2 would cancel out.
But you have it 2 squared. Okay. So they're really close, it looks like. That's not what we've got in other periods, but I don't know why we're getting something different. Do I have the thing right? Helium travels at velocity v. Yep. So they're really close. So which would have the greater kinetic energy? Well, barely hydrogen. Right? Okay, so going forward here. Like I said, I'm going to go through some of these really quickly. This conversion factor stuff up here is something I would write on my 3x5 card. This is something I would write on my 3x5 card. So 1 atmosphere is equal to 760 torr, is equal to 760 millimeters mercury, is equal to 101.3 kilopascals, is equal to 29.92 inches mercury, which is equal to 14.7 psi, which is pounds per square inch, which is equal to 1.013 bar. These are conversions from pressures. We're going to be using them a lot, and she uses them a lot. And she doesn't just stay in atmospheres, torrs, or millimeters. She goes to psi and bar, okay, and kPa. and inches mercury. She uses them all. So this is actually, if you don't have all this copied down, it's actually at the bottom of this next slide right here. I would like to show you how to use it if she has you do like this example. A weather reporter on the TV reports the barometer pressure is 28.6 inches of mercury. Calculate this pressure in the following units. So the first thing that we would do is we'd bring up our blank page here, and we would start with what we were given, which is the 28.6 inches of mercury. Okay, this is back to our regular old factor label. We're going to go like this, and then we're actually going to look at what we've got down here for inches mercury. So in inches mercury right here is 29.92. So that is going to go right here, 29.92. You guys want to grab that door? Inches mercury. Oh, thanks. She's going to do it. Thank you. Sorry. Okay. On the top, we want to get to atmosphere. So we would look down here and we'd find 1 atmosphere, and that would be what goes on the top. So all I would have to do is cancel out inches mercury, and I would take 28.6 divided by 29.92, and I should end up with 0.956 atmospheres. Now, to get the rest, all I have to do, it's going to be the same setup. I'm just going to be changing what is on the top. So instead of atmospheres, the next time I'm going to put what is in torr, the 760 torr right here. So this time I'm going to not just do 1 step, but I'll do 2. This divided by this times by this. And I spelled torr wrong. Okay? Would you quickly do the rest real fast? I'll leave this up as an example, but would you quickly do the rest, and I'll slowly put answers up? Oh, yeah, let me get smaller. It's as small as that window gets, sorry. Next one you would take and put whatever else you're trying to get to right there. You can check if you've got it right. I've got to put the answers up. This should be a very quick and easy conversion as long as you've got these somewhere that you can look at real fast. What you want to get rid of on the bottom, what you want to go to on the top. Just a quick factor label. Okay, I give you about 30 seconds left to finish up or write down the answers if you'd like to have the answers. Okay, moving forward. When we talk about pressure, we're talking about force divided by area. If you've had physics, you sort of know what pressure is all about and figuring out the pressure in an area. What causes pressure is the collisions of the gas particles with each other and the walls of the container. It's sort of like a crash on a car. The gas particle against the walls of the container, and we get pressure. When gas particles collide with the walls of the container, they exert pressure. And it depends on how big those particles are when they hit the wall, depends on the pressure. We've got all of these conversions except for this last one. It's pascals instead of kilopascals. If you want to add it to your equal, 101.325 PA, it corresponds to the 101.3 kilopascals, but you get 2 more significant figures. So 101.325 PA. So let's look at a ballerina. A ballerina, when she's flat, will exert a force of about 500 newtons in an area of about 325 centimeters squared. If we do force divided by area, we get 1.5 newtons per centimeters cubed, or squared. If she goes up on toe, the force is still the same, but the area of contact changes. And that changes the pressure. This is why a lot of ballerinas have really bad toes. If you go one more, when they actually go up on one toe, the force almost doubles. Okay? So the amount of contact is important. So if I have a small molecule that's moving quickly in a small area, that is different than a larger one moving at the same speed. Okay, so for the next few slides, I'm just going to talk it through. There's really nothing in your notes. I'll let you know when you go back into your notes. So just watch me up here. You've got original temperature, pressure, and volume. If I double the pressure or increase the pressure, I'm going to increase the temperature if I want to hold at the original volume. That's the only way I can keep the volume at the original place. If I let the volume go up, in order for the volume to go up, I'm going to have to increase the temperature also at the same pressure that it was originally. If I have a volume of moles, N is equal to moles, and I have a pressure coming down, I'm going to have a certain volume. If I double that number of moles to keep the same pressure, I'm going to have to double the volume. If I have triple that number of moles, I'm going to have to triple the volume to have that pressure remain the same. We know as we go from solid to liquid to gas to plasma, energy increases. And because energy increases, that means these molecules are moving faster around, hitting each other more, and there's more collisions. So some things that we need to observe about kinetic molecular theory. Gases have low density. They're far apart. A gas always exerts a uniform pressure on all the walls of its container because they're moving so fast they bounce around. Solids, liquids, and gases all expand when heated. So as we're looking at them, even when it's cold, if I heat something that's cold, it's going to start getting more excited. If I take a bottle of air and I just attach a balloon that hasn't been blown up, if I heat that bottle up, that balloon will blow up. Okay? It's not that I've changed what's in there, I've changed the kinetic energy that's in there and how they're moving. So let's look at each of these statements and decide if it applies to a solid, liquid, or a gas. The first one, temperature changes influence the volume of this state substantially. What do you think that belongs to? Solid, liquid, or gas? And these, I think, are in your notes too. Gas, good. In this state, constituent particles are less free to move about than in other states. Solid. Pressure changes influence the volume of this state more than that of the other two. Good. And this state is characterized, be careful with this one, is characterized by an indefinite shape and a low density. Gas. If it would have said a medium density or a density of about 1, it would have been a liquid. Okay? All right, so some characteristics of gas. They'll expand to fill any container. Random motion, no attraction. Gases are fluid, like liquids. They will pour like liquids. They have very low density, no volume, lots and lots of empty space. So as we look at it, solid, liquid, gas, we've got lots of space, but they're also moving a lot more. These would be flowing over each other, and these would just be jittering back and forth. Some characteristics of gases, they can be compressed. Okay? They basically have no volume, but they have lots of empty space. Gases undergo what we call effusion and diffusion. So effusion is through a hole, like a pinprick hole. So if I have a gas line and I have a pinprick hole in that gas line, the chemical they put in there for me to smell it, to know that there's a leak, is effusing through the hole and then diffusing through the area. So diffusing is like going through the room, randomly mixing with the room. Okay? But effusing is through a hole. So when you opened up the bottle here, because it's a bigger hole than a pinprick, it's called diffusion. If it was just a pinprick hole, it would be called effusion. But once it starts mixing with the room, it would be diffusion. Okay? It's because of the random motion. So when I change the size of a container, I'm squishing things together. So it's like if they took and moved this wall in and gave us only half of this room, it would put us all closer together. And the chances of us knocking into each other as we got up and moved around would be higher. And that's what happens with pressure. So in a small container, molecules have less room to move. They hit the sides of the container more often. This increases the pressure, and as the volume decreases, pressure increases. Pressure and volume are tied together. If I decrease the volume, it increases the pressure. If I decrease the pressure, it increases the volume. Okay, so they're tied together. All right, so here we start into the gas laws. We need to know some specific words. And I know this is a long day for lecture. I'll try and give you a little break here in just a minute if you'll stick with me. So STP is standard temperature and pressure. Notice the ones in red. You need to know these. You need to know what they are. So standard temperature, 273.15 Kelvin. Standard pressure, 1 atmosphere. And I've highlighted those. The 1 atmosphere is what we're going to want to use most often, and the 273.15 we want to use most often. The ones I've got grayed out will work in some forms of equations that we're going to be learning here in just a minute, but not all. Okay, so standard temperature, 273 Kelvin, standard pressure, 1 atmosphere. Ready to move forward? All these others you've got written down from earlier. But if you want to write 0 degrees Celsius, that's fine. We have 3 temperature scales we're working with: Fahrenheit, Celsius, and Kelvin. You need these equations right here. Okay? Fahrenheit was just sort of there, randomly made. 32 was freezing, 212 was boiling. Celsius came along and said, you know what, let's make this a little bit more make sense. So at 0, it's going to be freezing. 100, it's going to be boiling. There's 100 marks in between, evenly divided. And then they just used that mark throughout the scale. The problem came when we started to work with equations with Celsius. We would end up with something divided by 0 degrees Celsius. Well, if I take something divided by 0 degrees Celsius, what do I get, math? Undefined, error. Yeah, so that became a problem. It also became a problem when I had a negative number and I was trying to solve for volume. I ended up with a negative volume. That doesn't work. So what they did is they just added 273 to the Celsius scale, kept the same markings, divisions, and just made it an absolute temperature scale. So there's no 0. We've never reached 0 Kelvin. And there's no negatives. So we can use the math equations for them. Okay, so that's important. We always want to do gas laws in Kelvin. Always, 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 always. Okay, even when they ask for Celsius at the end. You've got to convert it into Kelvin and then convert it back out of Kelvin once you use the equation. Because of the negatives and because of the 0. Okay, so let's convert these really fast. See how fast you can convert them. 78 degrees Kelvin to Celsius. First one get it, raise your hand. See if you got it right. Okay, what is it? Good. Okay, next one, go. Again, first one get it, raise your hand. Yes. 329 is correct. So you should be able to do these very, very quickly is what I'm trying to point out to you. Going backwards and forwards from Celsius to Kelvin is just adding or subtracting 273, depending on which way you're going. Okay, 273.15. So very, very quick and easy. All right, we've got laws now that we need to learn. So this is the last part of the lecture today. We're just going to go through some laws and some examples real quick. If you remember this law, you'll be able to get all but 2 of the laws from this law. Okay? So, I'm going to give you funny ways to remember it, each law, and what is done with each law. And it might sound silly, but it will help you. Okay? Ideally, you're not a pervert. Okay, right? The ideal gas law is pervnert. PV equals nRT. Right. So you're trying to remember it. Ideally, you're not a pervert. Okay, PV equals nRT. So this will be at the top of the next slide, so don't freak out. It's up here. I'm going to go through each thing. So P is pressure. This is where the atmospheres becomes a issue. It's got to be in atmospheres for this particular law. Has to be in atmospheres. So you've got to be able to use your conversion factors to go back and forth very quickly. V must be in liters for this law. N is your number of moles. R is a constant. It's 0.0821 atmospheres times liters divided by moles times Kelvin. This is something I would probably put on my 3x5 card. And T has to be in Kelvin. Give you a few minutes to get that written down.
Like all this on the card?
Depends on how much you need to remember. I would put the conversions from atmospheres. I would put my gas law constant. From the gas law constant, I can see really quickly what I need to have all the things, the gas law in. I would put the gas laws that we're learning on the card, so I didn't have to try and remember them. But you get to put what you would like on your card. Okay, moving forward, let's try a problem with this. All the gas law problems are going to be story problems. So get used to reading and pulling out what you need and converting it right away. So how many moles, N equals question mark, of gas are contained in a typical human breath? So what? That takes in 0.5 liters, that's a volume, of air at 1.0 atmospheres, that's a pressure. And 37 degrees Celsius, that's a temperature. I also know that I have the R constant. When I write down the temperature, I go right away to converting it into Kelvin. So first I write down what I have, but the minute I see a temperature, I right away change it to Kelvin. Because I don't want to mistakenly put it into the equation and not have changed it. Once I do that, I rearrange. Now, this is up to you. Depends on how you like to do math. You can just put the numbers in, solve, and then find your one that you're missing, or you can rearrange it for the one that you're missing and then plug in. I like to rearrange it first and then plug in. You can just plug in if you want and then solve for what you don't have. Solve for it. Some of these are crossed out and shouldn't be, like the moles shouldn't be crossed out. The liters and Kelvin should be. Sorry, I did some mistaking stuff there. It's all right. But times the top, times through the bottom, make sure the bottom is in big parentheses there, and you get your answer. And then I can go back and look at the question, is that really what I was supposed to find? Yes. Okay? I'm seeing the head bob, so I'm waiting for a minute. Let me know when you're ready. Okay, going forward, if we take the ideal gas law and solve for R, R is a constant. So I can take two sets of data and set them equal to each other because R doesn't change. When we do that, we get what's called the combined gas law. This is the first of the laws that we can get from the ideal gas law. So P1V1 divided by N1T1 equals P2V2 divided by N2T2. So all we've done is taken the ideal gas law and solved it for R, and then set the two R's equal to each other. Everybody okay with that? Now, that's a lot of knowns. You would need to know 7 things to find one thing here, right? But oftentimes, in the combined gas law, we drop out N, because N is hard to change. And it's a lot easier just to leave it constant. So it drops out. So sometimes, most of the time you'll be using combined gas law, it will be like this, where N drops out. All right. The next law is Boyle's. So when you think of Boyle's, what do you think of? Boiling water, temperature. So think of holding temperature constant. So here we've got the ideal gas law, but temperature is held constant, so it drops out. This is Boyle's law. And I'm actually giving you these laws in reverse order than what it gives you in the book. They do it forward instead of backwards, but to me it's easier to find all the laws and understand them when you go the other way. Because then each of these laws were found individually, and then that made the combined gas law, and then they figured out the ideal gas law. Okay? So on Boyle's law, we have an example here, again, as you go through. And even if I think it might be the ideal gas law that I'm using, as I'm going through, I always say, oh, here's the first thing I'm pulling out. That's going to be V1. Because even if I say P1, V1, T1, and then find N, or I need to find N, then I know I'm using the ideal gas law. Doesn't matter if I have a number there or not. But if I end up with 2 volumes, then I know I don't have the ideal gas law that I'm using one of the others. So the caution I want to caution you here is as you're reading this STEM or this question, make sure that the ones that you give the same number to are actually tied together. So for instance here it says if a 4-liter container of helium has a pressure, so these two go together. What pressure does the exact gas exert if the volume is increased to this? So my P2 is my question mark, my V2 is that second volume. Okay, so they might just give you the first one, say at an initial volume of this, what is the pressure of when I had the, did it a little bit different. So your unknown is your first thing. So be careful there. So again, label everything you got, what you need. I like to rearrange. You can choose to just leave it here and plug in. Plug in once you've got this done. I believe it's the final answer is like 6.8 or 6.7, something like that. I forgot to put the answer on here. Any problems with this? Okay, basically, once you pull it out of being a story problem, all you have to do is plug in. Make sure the units cancel. Okay, so the next law that we're going on to, so like liters cancel would be in atmospheres, and atmospheres is a pressure. Oh, we did the application, I forgot. So the application of this, since this is a medical chemistry class, is breathing. To inhale, the rib cage expands, so the volume increases. Because the volume increases, the pressure inside the lungs decreases, and because of that, air is drawn in through your nose. Okay, to exhale, your rib cage contracts, it decreases the volume, your diaphragm moves up, decreases the volume of your lungs, and air is pushed out. Because the volume inside and outside has to be, the pressure inside and outside needs to be equalized. Okay, so the next law is Charles. When I think of Charles, I think of Prince Charles, and how he's under constant pressure from the paparazzi, trying to get pictures and trying to get things from him and wanting him to do certain things. So I think pressure. So as we look at the combined gas law, pressure is going to drop away. So anything that's held constant drops out of the combined gas law. This is Charles's law. Again, N could be on the bottom, but it's not. I don't know where my thing went. I guess I took the line there. That's supposed to be a line there. But it doesn't have to be. Remember, temperature must be in Kelvin in all these laws. Must be in Kelvin. Okay, going forward. Oh, went backwards, sorry. So there's Charles' law. Charles' law application is more of a weather application, but that does affect like asthmatics and stuff because of how dense the air can be. So cooler air is slower moving and it's about a higher density. So as you breathe in colder air, you're actually getting more oxygen than less oxygen in the same volume of air. As it is heated, it expands, it rises, and it becomes farther apart. Okay? So another law is Gay-Lussac's, and I call it Gay-Lussac's because it helps me remember sucking, volume, or through a straw. That has to do with volume. Okay, that's just how I remember it. So I like to think sucks like volume. So volume is held constant, and so it will drop out, and we end up with this as the law. Okay, so I'm thinking of her sucking up through a straw. That's going to have some volume. Again, N could be on the bottom, but it doesn't have to be. Okay, so we're just getting a whole bunch of laws right now. The next law is Avogadro's, and I'm going to sort of go quickly through these slides here because the Avogadro's law is at the end. But the main thing that you need to know here is basically the number of moles goes up, the volume goes up. Okay, and that he found out in 1 mole there's 6.022 times 10 to the 23rd molecules, which is equal to 22.4 liters. On each one of my walls, except the front one, there's a mole map. And on that mole map, right from the mole in the center going down, there is a way to get to volume at STP. It has to be at STP. So this is another part of the stoichiometry that we could use to change from moles of something to volume of something, or volume of something to moles of something. Okay? So I'm going to go through this real quick. This just shows 2 moles of different compounds, a mole of each compound, how they would have the same volume, the same number of moles, the same number of particles, but different masses. Again, another version of the same thing. And then we've got just basically saying that it's proportional. So we get this. And here's our law. Avogadro's law is V1 divided by N1 equals V2 divided by N2. So we have our initial conditions and our ending conditions. But basically, if I've got 1 to 1, then it becomes 2 to 2. They've got to end up being the same. Okay? Avogadro's law, if I'm going to use it with the stoichiometry, I have to do it at STP. And even if I'm using it here, look what's dropped out. Pressure and temperature, they have to be the same. Okay, so at standard temperature, I can say 1 mole is equal to 22.4 liters of anything. And that's known as a standard molar volume. Okay, so when I have a problem like this, how many moles are contained in 2 liters of N2 at standard temperature and pressure? We know this quantity. We don't know the moles. Okay, so what we're going to do is we're going to use this conversion, which is on our mole maps that is on the wall. For every 1 mole there's 22.4 liters, or for every 1 mole there's 22.4 liters. Since I was given liters, I want this fraction to put here, and I'm going to cancel out liters. 2 divided by this, and it gives me moles. So this is just standard stoichiometry. Are we okay with this? I know I'm talking really fast. I'm sorry. Are we okay? I'm almost to the break. Got 2 more laws. Got 2 more laws. You can hang in there. 2 more laws. Okay? The next law is Graham's law. And I remember this for Grandma. And the reason I remember it from Grandma is Grandma used to come and visit our house when we were at school, and then she'd leave, and we'd come home, and we knew Grandma had been there because her smell was still there. Okay, because she had really heavy perfume, and it stuck around. So this is rate or velocity A, velocity B, or rate A, rate B, is equal to the square root of the mass, molar mass of B, divided by the molar mass of A. Notice they trade places. This law just compares how fast things move. And we're going to do this law and Boyle's law next time. So in your lab, make sure you go over parts A and C along with doing your pre-lab before you come to class next time, so you know how to do those 2 parts. They're really fast, and once you get them done, you can be working on Learn Smart until we get everybody back in class, and then we'll do the lecture. So we're going to do lab first next time, so make sure you're ready. Okay? We'll be doing the lab in little bits and pieces, like one day we'll do this part, one day we'll do this part, kind of thing. And I'll let you know the day before what part. That's why you're getting it so far in advance. Okay, this is what we're going to be doing, but this is going to be a straw, and we're going to be using Q-tips. We're going to put on this Q-tip over here, we're going to put ammonium hydroxide. When ammonium hydroxide goes to a gas, it becomes ammonia. It leaves behind water. Over here, we're going to put hydrochloric acid. Hydrochloric acid goes to a gas as hydrochloric acid. When these 2 meet, they make ammonium chloride, and it's a white ring. you have to look for the minute that white ring appears. This ring is it's too late on this ring to actually do a good measurement because it started to spread. You want that ring when it first becomes a ring, when the two fronts of the two gases first hit and make that ring, because then they'll start passing each other and reacting with other things, and then you've lost their ratio of how fast they were compared to each other. But we're going to be marking that ring when it first appears, and then we'll measure from how far this Q-tip was in to that ring, how far this Q-tip was into this ring, and we'll set up a ratio. Okay? So remember the difference between diffusion and effusion. Diffusion is just how it's moving around in the classroom or in an area to get to the other side. Effusion is through a pinhole opening. Okay? To see how fast it moves through that pinhole opening. The last law that we're going to talk about today is Dalton's law of partial pressures. And it's a good thing it's the last law. I call it the duh law. Man, I wish I was alive and got credit for this. That's all I got to say. It's one of those laws you go, really? He got credit for that? Yeah, he got credit for this. It basically says the total pressure in any container is what you add up of all the little parts. Really, he got credit for that. So I went, okay, but we use it a lot in lab. We use it here. And the reason we use it is as we collect gas, we're going to be bubbling it through water. And as we bubble it through water, some of that water turns into water vapor, which then affects the pressure and how much volume of gas we've got. So we have to figure out what the temperature of the water is, what the vapor pressure of the water is, and subtract it from the total pressure in the room to find the pressure of the dry gas. So we can do calculations. So this is how we use Dalton's duh law the most. However, I want you to show you a problem on Dalton's law, just in case you didn't understand how duh it was. So here's a sample problem. Basically, we have a container, and it has the following partial pressures: nitrogen, oxygen, carbon dioxide, water. What's the total pressure of the sample? Add them up. It's not hard. Now, a variation of this would be, here's the total pressure, here's all these partials. I don't know what the pressure of this one is. Find out what it is. So add up all the partials, subtract it from the total, and you've got what's left over. Right? So this one is really easy. Now, I'm going to show you a trick real quick.
Pressure, temperature, and volume.
I've got to shut him up, though. Sorry.
If we imagine...
Okay. So if you take this, and this is something I would write on my 3x5 card too, because it will help me to identify if I've done a problem right or not. Okay, so if I'm holding pressure constant, okay, and I've got this thing, then if I have a volume, say I've been given two volumes, and I start with a volume that's low, but then it goes high, then my temperature, which was low, should have gone higher for my answer. This is whose law? Who holds pressure constant? Who's under constant pressure from the paparazzi? Charles. This is Charles' law. Okay, so whose law holds temperature constant? Boyle's, because temperature boils, right. So on Boyle's law, maybe I was given two pressures, and one was high and the second one was low. Then my temperature should increase. Okay? If I was given two temperatures, and one was high and the other one was low, you can see how it goes? So it tells me, okay, which one, if my unknown goes with this, where should I end up? If I didn't end up where I should have with this, then I did something wrong. I need to redo it. Okay, whose law holds the volume constant? Gay-Lussac's. Gay-Lussac's. Okay, so again, if pressure goes down, temperature goes down. If temperature goes up, pressure goes up. So this is a real quick, easy way. Did I get the right answer? And if I did, great. Because you know what? She's going to put all the wrong answers on there too, that you think you could get by forgetting to change temperature, Celsius to Kelvin. That answer will be there. Okay? So be careful. All right, so what I want to do, let me just show you what's next. On the next slide, we have got...
holding temperature constant.
We've got a whole bunch of problems. And what I'm going to do is I am going to put the answers to these problems up on your Canvas, so that you can use this to see if you can do it by yourself, and then you can go and check these problems step by step before you do your homework, so that you know how to do these. Okay, I don't want to waste time in class because I think we need the time for other things, but I want to have it accessible for you so that you can try the problems, make sure you know how to do them before you hit the test, and before you have the homework problems that you are held responsible for. Okay? Are you okay with that? We can go through one if you want. I'm okay with that. Or I can give you time right now, and that'll give you about a half hour that you can work on Learn Smarts, work on your pre-lab, work on the problems in the homework. Here are the notes that I've got, whatever you'd like to do.
Yes.
Yes, what?
Learn Smarts.
Learn Smarts? Okay, time is yours then. And we'll start at the end of the problems for the next notes. Okay? And I'll try and get those up tonight on the computer. Yeah, pre-lab, I would probably get that done first unless you want to do that on your own.